as we've seen, we're not always going to be able to find the exact sum of an infinite series. But we could always approximate our sum with a partial sum. So my sum to infinity, I'm going to switch from n's to k's so that I can put an n in. So my sum to infinity, I could think of going from 1 to n, and then n plus 1 to infinity. So if I look at just the sum of the first n terms, that's just this piece. Now if I subtract the two, so my sum to infinity minus my partial sum, then I'm going to get, this goes away. So expanding this, I'll start by plugging in n plus 1. So I'll have negative 1 to the n, a to the n plus 1, plus negative 1 to the n plus 1, a to the n plus 2, and so on and so forth. So let's say that our n is positive. Sorry, not positive, obviously n is positive. Let's say our n is even. So if n is even, then we're going to end up with a to the n plus 1 minus a to the n plus 2, a to the n plus 3, minus etc. Since it's convergent, we know that a to the n plus 1 is less than a to the n. So that tells me that a to the n plus 2 is greater than a to the n plus 3. So this is some sort of negative quantity, and every pair after that will also be negative. So I'm going to end up with a to the n plus 1 minus a whole bunch of negative quantities that I could call k. So this is one way for me to think that my difference in my actual sum and the approximation is going to be less than the a to the n plus 1th term. I take the absolute value because I don't know whether my approximation is going to be less than the sum or greater than the sum. And I started this by saying that n was even. The same thing is going to hold true even if the n value is odd. And I'll leave you to think about that. But we can sum this up with our statement here that for any convergent, so it has to be convergent, right, alternating series of this form, then my remainder, if I take the actual sum and subtract an approximation, will be less than or equal to the next term. That's going to help me answer questions like this. So again, if we want accurate to 2 decimal places, then that means we want r sub k to be less than 0.005. So that means I'm going to want the n plus 1th term to be less than 0.005. My n plus 1th term, 1 over n plus 1, just looking at the a sub n's, well, that's going to turn into, what is that going to become? 5 thousandths? No, 1,000 out of 5, which becomes 200. So then n needs to be greater than 199. Therefore, I need 200 terms. 200. So accurate to 2 decimal places, even though this is less than or equal to this term, I want my remainder to be less than 0.005 so that I am rounding correctly. So I'm actually going to want to take the 200th term.